Okay, so let's look at this first question where she gave you a graph and asked you to calculate the integral of various things. So I want to find the integral from 1 to 3 of f of x dx. So again, right, you're just trying to find the area under the curve. The only thing that I think might have been hard about this first one was not knowing how high this triangle is necessarily. Now, you can pretty easily, I think, justify to yourself that this line has a slope of -1, right? You can either just kind of see it, or you can say, hey, that point is definitely 4, -1. This point is 0, 3. So I went over 4 and down 4. That's a slope of -1, which I feel like helps me more strongly know that, oh, if this is a slope of -1, then if I go over 1 and going down 1, so that point there is the point 1, 2, which means that the area under the curve from 1 to 3 is going to be the area of this triangle, which is the 1/2, the base, which is 2, times the height, which is also 2, which is going to be 2. So that first area looks like it's 2. That first interval is 2. The second interval, the interval from 2 to 5, that's going to be this area, the area of that little orange triangle there, minus this area in blue. So that looks like it's going to be, so the area of the orange triangle, so just like this is the point 1, 2, this is the point 2, 1. Because again, right, for this first section, every time you go over 1, you go down 1, right? The slope's -1. Chang, if you're joining us, Chang, we're just going over the quiz from class today. So to find the integral from 2 to 5, you're going to say, well, the area of that orange part there is 1/2 base times height, which is 1/2 1 times 1. The area of this blue part here is going to be subtracted, and it's going to be, so the area of that square is just 1, right? It's a 1 by 1 square. And the area of that triangle is 1/2. It's a 1 by 1 triangle, so it's a 1/2 of 1 times 1. So you end up getting 1/2 minus 1.5, which is going to end up being -1. And then for the integral from 8 to 11, so it looked like when I looked at the picture, I'm pretty sure it seemed to be true that the point above 8 had a height of 3. That was 8, 3. And so did the point above 9. And then from 9 to 11, it went down. Again, with the slope of -1, right? From 9 to 11, we go over 2 and down 2. So then we can find all of these areas. You can do this kind of anyway. I was thinking of it kind of like this, where I might break it up as this rectangle with a base of 3 and a height of 1, plus this rectangle with a base of 1 and a height of 2, plus this triangle with a base of 2 and a height of 2, which is 1/2 times 2 times 2. So that would be 3 plus 2 plus 2, which is 7. So that's how I would do this first problem. And that's what she wanted to do, right? She just wanted you to use areas of triangles and things and rectangles and squares to figure out how much area is under the curve but still above the x-axis, right? This second piece, that part down below here has to get counted as negative. Okay. The only thing I think that was hard about this problem was knowing exactly like how tall the triangles were. That was probably the hardest part. Are there any questions about this one? Got some new pens. Good to go. All right, let's look at this one. So this one, I think she gave you the formulas for, but she said use the formulas to find what this adds up to. Now, I feel like this n here might throw people off a little bit. You're not actually going to get a final answer, or you're not going to get a numerical answer. You're going to get just something with an n in it. Maybe some of the n's will cancel. I don't know. But here's what I think we want to do. We want to break this up. I don't think I might have given myself quite enough room here. I want to break this up as the sum from I equals 1 to n of 6i squared over n minus the sum from I equals 1 to n of 2i over n. Yeah, that's kind of funny. That's all right. And then we're going to factor out any constants that are not I. Meaning I'm going to write this part here as 6 over n times the sum of I squared. minus, this is going to be 2 over n times the sum of I from I equals 1 to n, I equals 1 to n. And then, I'm going to erase a little bit here. And then we get to use the formulas for these sums. And this is equal to, well, the sum of I squared is n times n plus 1 times 2n plus 1. Oh, this is a sneaky problem. I see what she did. N times n plus 1 times 2n plus 1 over 6. And look, you can cancel a 6 and an n. And this one is 2 over n times the sum of I is n times n plus 1 over 2. So you can cancel a 2 and an n. So if you simplify this problem as much as possible, you get n plus 1 times 2n plus 1 minus n plus 1. Which you could then, you could multiply. I don't, like, I would, if I was doing the quiz, I would have stopped there, done the rest of the problem, and then gone back and simplified this if I wanted to. But if you want to simplify this, it's going to be 2n squared plus 3n plus 1 minus n minus 1. So it becomes 2n squared plus 2n. It's kind of a neat little result. I mean, it's not like special or anything, but kind of cool. Okay. Please stop me if you have questions. Also, my volume is on. Yeah. Okay. Yeah. Sometimes I said that and I had not my volume on. People are like, James, we're saying things, but you can't hear us. So my volume is on. This last one, not this last one, the next one here. So it's given that the sum from I equals 1 to 9 of a sub I is equal to 3. That just means that a1 plus a2 plus a3 plus a4 all the way up to a9 adds up to 3. We don't know what any of the individual pieces are, but we don't need to. So the same kind of thing that we did here, we're going to do here. We're going to break this up into the sum from I equals 1 to 9 of 7/3 minus the sum from I equals 1 to 9 of a sub I. When you sum a constant, right, so you're doing 7/3 plus 7/3 plus 7/3 plus 7/3 9 times. So you're going to get 9 times 7/3 minus, when you do the sum from I equals 1 to 9 of a sub I, we know that that's equal to 3 because that's what we've been told. So you get 9 times 7/3 minus 3. 9 times 7/3 is 3 times 7, which is 21 minus 3, which is 18. Okay. I would say this quiz looks relatively challenging. Like this would certainly be hard to do in. I know there's one more problem. I would say this quiz would be hard to do and get everything right in 24 minutes, but not totally unreasonable. So I think she gave you guys a fair quiz, although certainly a challenging quiz. So let's look at this last one. So the car has a velocity that is given by v of t equal to 45 plus sine of t. And I believe the problem also says, although it's not on my thing anymore, I believe the problem says that the initial position is 0. But let me double check just so I can make sure I'm saying the right things. The initial displacement of the car is 0 miles and t is measured in hours. Okay, cool. So if I want to find the position function, I'm just going to anti-differentiate the velocity function. So the antiderivative of this is going to be 45t plus cosine of t. I'm sorry, minus cosine of t, right? The antiderivative sign is negative cosine plus c. So this was kind of a hidden initial value problem, right? Because she's giving you the initial, she's giving you the velocity, she's asking you to find the position, but she's also told us that at time 0, the displacement is 0. So when t equals 0, s of 0 is 0. Meaning when I plug in t equals 0, it should equal 0. So 45 times 0 minus cosine of 0 plus c equals 0. Which means c is going to equal 1. Because that's 0, but cosine of 0 is 1. So that's going to tell me that negative 1 plus c equals 0, so c equals 1. So the actual answer to the first part of this, to the part A of this, is that the position function is 45t minus cosine of t plus 1. That's our position function. And then I thought the second part of this was a good question to get us to think about what things look like. So the second part said, she basically asked you if you were to use 4 rectangles to estimate or approximate the distance traveled in the first hour, and you used rectangles as right endpoints, would you get an overestimate or an underestimate? Or I feel like she might have said, yeah, would your estimate be exact, an overestimate, or an underestimate? Sketch the graph and the rectangles. So here's the graph, and now we're graphing 45 plus sine of t. So I tried to graph almost the whole period, right? A period going from 0 to 2 pi. I didn't go all the way, right? 2 pi would be like over here. So 45 sine of t, sine starts at 45, right? Sine of 0 is 0. And then at pi over 2, sine of pi over 2 is 1. So we go up to 46. And then at pi, sine of pi is 0. So we're back to 45. And then 3 pi over 2, we're back down to whatever 45 minus 1 is 44. Yeah. And then we'd be back there. Now, the important thing to know here is that time is measured in hours, and pi is 3.14, pi over 2 is 1.5 something, and 1 hour is less than pi over 2. So even though this function is increasing then decreasing, right? It fluctuates between being an increasing and decreasing function. The interval that we are looking at from 0 to 1 is purely increasing, which means that every rectangle every rectangle's area is going to be an overestimate if we're using right endpoints, and we are. So this rectangle, if we use the right endpoint, we're using the biggest point in that interval, it's overestimate. So is every rectangle in this interval. So the whole thing is going to be an overestimate. So yeah, if you have an increasing function using right endpoints, you're going to need an overestimate. In fact, this is something I should just say this blanket statement. Increasing right endpoints, overestimate. Decreasing left endpoints, overestimate. Right? If you had, I'm going to draw it. Good. All right, so in the same sort of way, if you had a function that was decreasing and you want to find the area or estimate the area using rectangles with left endpoints, right? This first rectangle here, or this first interval, if I use the left endpoint, overestimate. Left endpoint, overestimate. So if you're decreasing using left endpoints, you're also overestimating. And then the reverse. If you're decreasing and using right endpoints, you're going to be underestimate. And if you're increasing using the left endpoints, you're going to be an underestimate. And then if you're fluctuating, it's really not very easily knowable if you're under or overestimating. So yeah. Oops. Okay. So that's all I have to say about the quiz. Do you guys have any questions about that before we move on? Hopefully it went all right. I mean, I can't imagine she's graded them yet, obviously, but hopefully you felt like it went okay. Erase the backside of the board. So I think it's perfectly reasonable for us to start talking about the fundamental theorem of calculus, or at least to kind of get you ready, because I'm sure that's kind of the next section. So it never hurts to get ahead, unless there's any questions about your guys' homework. If you do have questions about the homework, I'm happy to address them. If you don't, I'm going to go ahead and start talking about the fundamental theorem of calculus. Do I want to draw this picture, or do I want to just show it to you guys? Yeah, let's draw it. Okay. So I'm going to draw you guys a picture, and I'll try and do the best job I can. So suppose that, I shouldn't use V, but okay, fine, F. Suppose that F of t equals the velocity of a runner at time t. Obviously, I wonder if people are taking notes. Like, It seems weird to be taking notes if you can watch the video later, but taking notes is definitely a good way to learn things. So I'm not saying you should or shouldn't be taking notes. I'm not even asking you if you are. I'm just kind of curious. Oh, you have a question on the discussion sheet? Sure thing. For 2D, the discussion sheet. Let me take a look. I don't remember where to find the discussion sheet. Let's see. 1 minute. I think I know where it exists. Let's see, that's not the discussion sheet. Sorry, one second. I always happen to have things up that are covering up the chat, so I will try to not do that because you guys actually write things in the chat. Let's see here. While I'm looking for this, I should point out that I am going to post a quiz. It's not optional. I mean, it's optional, but like, right, you should do the quiz. Obviously, if you do it, you get the credit. So that'll be posted up sometime later today and due by Tuesday at noon or something. It's not a big deal. Just do your best. Okay. Sorry. I'm still trying to find the thing. I'm looking under assignments for Burke, and then I'm in the wrong class. That's real smart. There we go. Okay. So let's see. Assignments. Is it group work, worksheet 2? Is that what it is? Yeah, okay, cool. Let me take a look. Sorry, I think I'm going to get there. Okay, so looking at 2D. Wow, there's a lot to problem 2. It's kind of a lot. Okay. Okay, so let me look at this question because sorry, so Emily was asking about question 2D from the discussion. It looks long, so we'll talk about it and then we'll write down stuff as we go, and then we'll come back to this. So the concept of integration introduced through a simple example. Imagine that you and a friend are driving on a highway. Suppose that you wish to determine how far you've traveled, but your odometer is working. The car's speedometer works and you have access to a stopwatch. Given these tools, how would you figure out how far you've traveled? Okay, so if it was constant speed, right, you would just take your speed and multiply by the time. So if you traveled 30 miles an hour for 2 hours, right, you would do 30 times 2 to get 60 miles of distance. And then she says case 2, if you drive 60 miles for some time and exactly 30 for some time, you could obviously multiply the amount of time you went 60 miles per hour by the amount of time, and 30 by its time. Okay. Now, case 3 is where things start to get a little bit wonky. Part C. Continually varying speed, of course. For example. Okay. Oh, that's a lot to. Okay. So reality, case 4. Normally, one does not know how velocity varies with time. However, if your passenger has a stopwatch and can see the speedometer, they could measure it. Suppose that your friend makes the following measurements at the following times. In fact, you guys can see this, right? I can share it if you want, but everyone is also has this at their disposal somewhere, I'm sure. So, right? So suppose your friend makes the following measurements at the following times. If you make the simplifying but slightly incorrect assumption that speed is constant in between measurements, that is, your speed is exactly 60 miles per hour for the entire time between minute 0 and minute 1. Okay. How far would you have gone at time t equals 30 minutes? Okay. Okay. So, I see. Sorry. I'm trying to calculate the first bullet point and the third bullet point. Okay, so the first bullet point is asking us to, so to calculate the first bullet point, and it might not be any different. So here's how you calculate the first bullet point. And I'm not going to obviously do the whole thing, but here's how you do it. So for minute 0 to 1, I'm traveling 60 miles per hour. For minute 1 to 2, I'm traveling at 62 miles per hour. For minute 2 to 3, I'm traveling at 65 miles per hour. And we'll do one more. From minute 3 to 4, I'm traveling 72 miles per hour. Okay, so approximately how far did I travel in these 4 minutes? Well, I traveled 60 miles per hour times 1/60th of an hour, right? That's my miles per hour. In fact, you can even write it like this. So it's 60 miles per hour times 1/60th of an hour. The hours cancel, you get 1 mile. And then for the next minute, you traveled 62 miles per hour times 1/60th of a minute. And then for the next one, 65 miles. So each interval is 1/60th. So really of an hour. So what you can really do, at least for this first question, is just add up all of your measurements from 0 to 29 and then divide by 60. Because each of those measurements was for 1/60th of an hour. If we do it here, so I'm going to get 60 over 60 is 1, plus 62 over 60, plus 65 over 60, plus 72 over 60. That's going to add up to some number that's going to be slightly bigger than 4. 1 plus 62 over 60. Don't be stupid, James. I should add up 62 plus 65 plus 72 and then divide by 60. That's much easier. So that's going to give me 4.316666 approximately. So in those first 4 minutes, I went about 4.3 miles. So then what's the difference between this and the third bullet point? As you know, when speed is constant, distance traveled is speed multiplied by time. Thus, for example, the distance traveled in the first interval is approximately 60 miles per hour times 1 hour per 60. Yeah. By the area rectangle, the height equal to speed. Sketch in each of these rectangles in the previous plot. Since each rectangle's area is the distance traveled in that interval, given the area of each rectangle, how do you determine the total distance over the full 30 minutes? Totally the same question. And I think that's the point. The point is that she's trying to get you to see that the area under the curve is giving you the distance. So it's good that you recognizing like why, like I understand being confused on the difference between them because there isn't a difference between them. They're the same. So that's what's going on there. Hopefully that's clear to other people as well. That what I'm saying anyway. So yeah, so just in case everyone's not clear on that, right? She then Burke plots the data for you. So there's all of your little points. And then she's asking you to find the area under this using rectangles with, I guess we're using rectangles with left-hand endpoints, right? Because we're using the left point to get the height of the rectangle. There was a word I was going to say. And yeah, so then when you find the area of those rectangles, it's literally the same thing as finding the time times the velocity, which is what we're doing really, right? If you think about the area, like if I was to, in fact, I can actually draw the rectangle. I have a board right here. If I was to, oh, come on, right? So if like here's 60 and here's 62, right? So and here's 1 minute and here's 2 minutes. My first rectangle has a height of 60 and a width of 1 minute. So it's 1/60th of an hour times 60 miles per hour. And then the next rectangle, looks like that. And it's exactly 62 over 60. So yeah, good question. I'm glad you asked. But I definitely will say that most of Burke's handouts, as I'm sure you guys know from last quarter, right? She's really trying to drive home the point of like what things mean and what's going on with what. So yeah. All right, cool. Other questions about homework, worksheets, anything? I mean, anything math related. All right. I'm going to do one other thing here just so that you guys can all have this. Just in case you're curious, this is these are the notes that I'm working from today. They might be worth actually looking at on your own if you want. I'm going to explain things as well, but I'm going to be saying a lot of the same words that are on that handout. And hopefully drawing pictures that are almost as nice. So suppose f of t is the velocity of a runner at time t. So, right, maybe I'm running 5 miles per hour, maybe I'm running 6 miles per hour, maybe I'm running 7 miles per hour. That's about as fast as I can go, 7 miles per hour. Maybe 8 sometimes on a good day. Then the area under f of t. So this is very much related to literally what we were just saying with the question that Emily asked, that the area under the velocity curve is going to give you the distance. The area under, I want to be very specific with my notation. The area under y equal to f of t represents the distance traveled by the runner. Specifically this. And I think I want the picture too. So I'm going to draw the picture, I guess, on the other side here. I'll come back to that other side in a minute. So this picture is kind of super important. So yeah, here's my picture. And, here's my running. So, I start off running kind of fast and I speed up, and then I kind of I hit a maximum speed, and then I kind of slow down for a bit. I'm kind of tired, and then I maybe speed up again, right? So there's my velocity, right? So the y equals the velocity of the runner in, let's say, meters per second. Although I would probably measure it in feet per second. And right, f of t equals velocity at time t. And then on the x-axis, we have time. Let's say this way. So here's time equal to A. Here's time equal to B. And so the area under this curve would be how much distance I had traveled from t equals A to t equals B. Time is measured in seconds. Now, what I really want to look at is well, actually, I'm going to come back and draw that. Yeah. So I kind of want to look at one small sliver, kind of like a little rectangle, right? So this little rectangle, I want to point out that the area, well, let's see. So the area represents a couple things. The area of this is equal to the base times the height. The base is measured in seconds. The height is measured in velocity, which is in meters per second. So the area, the time units cancel and we get meters. Sorry, I keep doing this dumb thing where I'm covering up the chat, so I have no idea if anyone's typing anything. Oh, sorry. Thanks, Emily. Good call. Yeah. Thanks. Appreciate that. And so here's what I really want to say. I'm going to let that's interesting. Yeah, I knew I did. I knew there was something. I'm sorry. Let me. Sorry. I wanted to call y something different. Sorry. This is just f of t. Apologies. It's not a huge deal, but it is a small deal. The area under f of t. Okay. So here's what I actually want to call y. I want to call y the integral from a to b of f of t dt. So y is just the area under the curve, right? All this area that's equal to, oh no, sorry, I keep making small, tiny mistakes, so they're bothering me. It's not a huge deal, but instead of saying from A to B, I actually want to go from A to X. Sorry about that. so that I'm actually doing the integral not from a to b, but from a to x. There is a really good reason for this. So y equaling the integral from a to x of f of t dt. This is just the total distance traveled by the runner from time equals a seconds to time equals x seconds. So this is, right, this is from time equals a to time equals x. Okay, here's kind of the big deal. This next part is super important. I want to find the derivative, dy dx. Well, here's what we know. Y is the distance traveled as a function of x, right? Y depends on x. If x is further to the right, then we get more distance. If x is further to the left, we get less distance. But y certainly depends on x, so we can differentiate it. And dy dx, well, if y is the total distance traveled, then dy dx is the rate of change of the distance traveled. At when you get to time equal to x. Okay, well, I'm going to say this another way. The rate of change of the distance traveled, the rate of change of the distance is just another name for the velocity. So this is equal to the velocity of the runner at time equals x. But we know what the velocity of the runner is. The velocity of the runner is f of t. So that this is actually equal to damn room f of x. So here's what I've said. If you take the integral of something and then differentiate it, you get back the function inside. That's the whole kind of idea here, right? F of x or f of t was the velocity of a runner at time t. The area under f of t between a and x was the distance traveled. And then the derivative of the distance traveled, the rate of change of the distance traveled, is just the velocity. But if we look at it as an integral, right? If the area is the integral from a to x of f of t dt, then the derivative of that at t equals x is just f of x. Okay, it's a lot of words to say the following kind of result. What we're really saying with all of this is that the derivative of the integral from a to x of f of t dt, and that's exactly what we were looking at right here. Y is the integral from a to x of f of t dt. The derivative of the integral, the derivative of y, was equal to f of x. And I should point out that in this context, this a down here, that's a constant. It doesn't change. But the x up there is meant to represent a variable, right? This x here can be kind of anywhere. So that's the idea here, is that the derivative of the integral of a function is equal to the function. That is the fundamental theorem of calculus part 1. It's probably the part that we use less often, but it's definitely something we do use and talk about. So let me ask you guys, before, we're definitely going to do more here, but are there questions about this particular example? Or this particular, are there questions about anything I've said about this so far? Okay, if there's not, but I just want to kind of pause for a sec. Okay. So the idea with this is that you can use this fundamental theorem of calculus to then take the derivative of integrals. So for example, if I wanted to find the derivative of the integral from -2 to x of t squared dt, which you might think seems kind of like weird, like why would you do this? We can graph this if we want. All right, let's see, a -2, let's say that x is somewhere like here. All right, so we're saying, here's some x. This area is a function of x. And the rate of change of that function of x is just equal to x squared. It's kind of weird. You say that the area as a function of x is a function of x. Yeah. I want to say, there's something else I want to say, but I feel like it's kind of circular reasoning, so I feel like I shouldn't. But so this is kind of the whole idea, is that you can just straight away say the derivative of the antiderivative from a constant to x. I said antiderivative integral. The derivative of the antiderivative from -2 to x of t squared is just x squared. And this works for any function. If I want to find the derivative of, say, I don't know, the integral from 7 to x of sine of t over t dt. It almost starts to feel kind of silly, right? Like, well, I'm just getting the function that's inside the integral. Sine of x over x. Doesn't feel particularly exciting. Yeah, I kind of want to go this way, I think. So I'm going to go this way, and then we'll come back to these problems, because I feel like there's something I want to be saying here. Oh, we've only got 10 minutes left. Okay, I'm going to go kind of quick. I'm going to talk about the fundamental theorem of calculus part 2, which is much easier than the first part. And then we'll come back to some of these questions again. This is actually, so the part 2 part is really the part that's important. So check this out. Everybody really tune in here for a second. So we know that the derivative of the integral from a to x of f of t dt is equal to f of x. Again, a reminder, a is a constant, x is a variable, and t is what we usually call the dummy variable. So now let's anti-differentiate both sides. Well, if I'm anti-differentiating, right, if I'm anti-differentiating this side, I'm just getting rid of the derivative. So the antiderivative of this is just the integral from a to x of f of t dt. And the antiderivative of f of x, we usually call capital F of x plus c. Right? This is the antiderivative. Okay, so now check this out. Everybody should know the answer to this next part. What's the integral from a to a of f of t dt? You can type it in the chat. Right, exactly. If the limits are the same, you've got no area. Okay, well, I plugged in a for x here. I also have to plug in a for x here. But we just said that's equal to 0, which means that the constant here is equal to negative capital F of a. So whatever the antiderivative is, c is equal to the negative of the antiderivative evaluated at whatever a is. Okay, well now check this out. This is the cool part. So I just found that the integral from a to x of f of t dt is equal to the antiderivative of x plus negative f of a. Well, now I'm just going to replace the x with a b. So the integral from a to b of f of t dt is capital F of b minus capital F of a. This is the fundamental theorem of calculus part 2. And here's what it says. It's also called the evaluation theorem. It says that if you want to find the area under the curve f of t, I really should say the integral of f of t, right? Because it's not always technically area, right? If it's below, it's the net area above the x-axis. But if you want to find the area under the curve, f of t, between a and b, you take the antiderivative of f, you plug in the top value and subtract, and you plug in the bottom value. That's kind of great. So no more of this limit of craziness stuff or using area formulas. We can say that the integral, for example, from -2 to 3 of 2x plus 1, although we could use an area formula to find it because it's just triangles and rectangles, I can say, well, I know how to anti-differentiate this. The antiderivative of 2x is x squared. The antiderivative of 1 is x. And I could throw on a plus c. We don't usually, but I will this one time. So there's my f of x, my capital F of x. This is lowercase f of x. And then what we usually do to write f of b minus f of a is we usually write evaluated with a vertical line from a equals 2, sorry, -2 to b equals 3. So then it's always the b one first, always the top one first. So that's going to be 3 squared plus 3 plus c minus, now we plug in the a1, -2 squared plus -2 plus c. And look at what I get. I get 9 plus 3 plus c minus 4 minus a minus -2 is plus 2 minus c. Notice that the c's cancel. So I end up with 12 minus 4 is 8 plus 2 is 10. So a couple things to take away from this. One, you don't need the plus c. We don't need the plus c because they're always going to cancel out. Because it's always going to be plug in the top one, subtract, plug in the bottom one. The other thing to take away from this is that we could verify this if you want. If you look at the graph of 2x plus 1 from -2 to 3, let's see, 2x plus 1, it looks kind of like this. So at -2, when I plug in -2, I get -3. When I plug in 3, I get 7. So what this integral is calculating is the net area above the curve. So this triangle here minus this triangle here, which this triangle here has a height of 7, a base of, I have to find that intercept. It's going to be a base of 3.5, right? Because that point there is -1/2. So the area of this triangle is 1/2 the base, which is 3.5, which is 7/2 times 7, minus this one over here, which is going to be, so the length there is 3/2. The height there is 3. And then there's also the 1/2 I'm forgetting. And this ends up being, hopefully the right number, 49 over 4 minus 9 over 4 becomes 40 over 4, which is 10. So it does work, right? I'm not like pulling your leg or anything. Why would I do that? So this idea here, this evaluation theorem, this fundamental theorem of calculus part 2, is really how we evaluate definite integrals. we find the definite integral of a function, the area under the curve, by finding the antiderivative and then plugging in the top limit minus the bottom limit. It is also the reason why we use this symbol, this integral symbol, to also mean an antiderivative. So after this, you'll see that people will start saying things like, if I want to find the antiderivative of, say, x squared plus e to the x, I'm going to write it like this. Because if I'm finding the integral, the area under the curve, I use the antiderivative and then I plug in the endpoints. So if I just want to find the antiderivative as a function, I just write it like this. And then the antiderivative is going to be x cubed over 3 plus e to the x plus c. On the other hand, if I want to find the area under this curve, x squared plus e to the x, from 0 to 1, I would then anti-differentiate into these. I would get x cubed over 3 plus e to the x. I would leave off the plus c because I don't need it. And then I would plug in the limits of integration. So I plug in the top one first and get 1/3 plus e to the 1 minus, then I plug in the bottom one, I get 0 over 3 plus e to the 0. This would end up being 1/3 plus e minus 0 plus 1. So that'd be e plus 1/3 minus 1 is e minus 2/3. So that's the big idea with the fundamental theorem of calculus. Well, those are the big ideas with the fundamental theorem of calculus, is that one, if you take the derivative of the integral, when you're doing like the derivative of the integral from 2 to x of whatever function you want, like sine squared of t dt, you just get the function inside, but it's now a function of x. And the other big deal is that when you want to find the area under your curve, you're going to find the antiderivative of your function and then plug in the limits of integration. That's the fundamental theorem of calculus. I'm sure we will talk about this way more next week.